Is this thing actually working?
Hey, what's up, bud? I can see you.
I don't have a camera on my government laptop.
Well, that's a problem.
Well, good news is that my face doesn't get me a PhD. The data does, and the data's on the laptop. So
Fair enough.
what I wanted to show you, can you see the MATLAB figure that I have plotted there?
Mm-hmm.
Okay, so that's my raw data. 0 is the center line of the impact point at the orifice, and then the axis is a little screwed up, but it's the points are the velocity values. I didn't do a bar chart or anything, but they're actually they correspond to actually entrainment velocity. And so my question is, or going forward is
What's the bottom axis?
It's the orifice orifice location. So 0 would be the center point of the orifice, and negative 100 would be the top of the orifice, and then positive 100 would be the bottom of the orifice.
So this is exactly 1D?
No, it's a little short. It's about 100 pixels short of 1D, actually, because of the I hit high on this shot, and so I wasn't able to get a full orifice characterization across it. So I'm missing the top third of the orifice. So what I did is I went to the center. I created what symmetry I could have at the around the orifice.
And then is it where is it in the X location?
About a half a diameter downstream of the orifice. So I took at the orifice plate, and
Okay.
then I went right at 0, and then about a half a diameter downstream of the orifice is all. So it's relatively very close to the orifice.
And this is meters per second?
Correct.
Okay.
And so so my question, or going forward, is because there isn't a good velocity going forward, and so I mean I have a very I guess a noisy data, which is to be expected considering it's raw data. And so but I can.
And this is one shot, correct?
Yeah, this is just one shot, 0.9 milliseconds after impact.
But it's 2 frames.
No, this is the streak. This is just the streak data. So it's one frame.
So this is one image.
One image, a duration. Essentially, you're looking at the velocity data over a duration of 20 microseconds.
Okay.
And so what I want to do is, since there isn't a really good velocity, I want to fit a spline, like a cubic spline or smoothing spline, and that's the red line that you're seeing there.
Mm-hmm.
And then I could actually take that function that fits the data, and it fits the data reasonably well with an R² of approximately 70%. And then I can take that function, that velocity function, that gives me a velocity function as essentially in meters per second as a function of wherever I am on the orifice. And then I can take an integral using rho v and then the area of the orifice, and then I'll take a velocity, and it essentially sums over the mass flow rate over the orifice for that instant in time, since I don't have a good solid velocity to utilize. Does that make sense?
Yeah.
And so I can integrate piecewise, and that'll give me an m dot for this image, and then I want to progress through the entire set of images. And so if I can show you this. Hang out. AFIT got commercial Wi-Fi, so that's what I had to switch over. I was working on my office computer, and then I had to switch over and go to my laptop so I could use the commercial Wi-Fi. But it's actually working a lot better than I thought it would.
So after I leave, they get fancy new things like Wi-Fi.
Oh, it's great. I mean, I got Wi-Fi on my smartphone. I can go to the App Store and download apps. So,
but continue, because I've been begging for that for years.
Yeah, it's been pretty revolutionary for, like, because students are going to figure out ways to use stuff, right?
Yeah.
So it's pretty revolutionary for the students to have, commercial access to everything. So, right here this is the curve fitting tool in MATLAB, and so I mean it's actually kind of nice. So I fit a second order polynomial. It fits horrible, but it does have the right general slope, and that's what you're looking at. You're looking at right there. Um, but if and then the smoothing spline, that's what the figure that I showed you previously, and I can go a rougher mesh and fit all the data really well, or I can go smooth, and then eventually it just comes out to about the second order polynomial, kind of close or the same general shape. If I smooth the data out, and so that's why, because I'm at this crossroads, and that's kind of what I wanted to discuss with you today, going forward. Uh-oh, you frozen? Hello? Hey. Uh-oh, can't hear you.
Into hello?
Are you there?
Yeah, I'm here.
Okay, good
I'm
deal.
gonna drop my other laptop.
Okay.
All right.
All right, I gotta get back to. I assume you can't see anything. You just got a black screen because of my screen share drop.
Well, it's not black. It's got the Google symbol on it.
Yeah.
So the other thing that I saw, are you just planning to use one image to correlate your data?
Oh no.
Okay.
I'm gonna go through. I'm gonna process the entire image set. This is just. You're just looking at one instant in time, if you would.
Okay.
And so, can you see the curve fitting tool in MATLAB?
Yep.
Okay. So, I played around with the curve fitting tool last couple days. Try to get an idea of how to calculate that velocity profile to run the integral, and I'm messing with it now. And as you can see, as I get rougher, it fits more of the data. And if I get smoother, obviously the velocity profile fits more to like as you'd expect for the entrained flow field. And so
So before you keep going on that, my question is, if you're just integrating, why do you want a function? Why not just discretely integrate?
you're talking just because the data is sparse. So I don't have a full data set that covers every area. So
I know. So in space, you're gonna have to make it bigger, but in time, or in velocity, it's okay.
so you're saying, for example, like oh, actually okay, so like right here in the middle, right around 0, I have 2 points, but I don't have any other points until about -20, until about -18, right here where my cursor is.
Mm-hmm.
So you're saying just integrate, use these 2 points to apply it for a velocity for an area from essentially -15 to about 10.
Well, I would have used the trapezoidal rule, but it'll probably come out to a wash anyway, since the edges you have more data.
Okay. So you're basically, you're saying use the data I have and just integrate instead of trying to smooth the function out and find a continuous function and then integrate it.
Yeah, I mean that's what I would do, and that's what typically people would do, because then if you use a spline, then you have to prove why the spline is physically true.
Whereas the data is just the data.
Correct. You're just integrating based on the data you have, and then you can calculate your error terms, right? Your standard error, and then you can say, hey, I have confidence of this data up to this point, and the more sets of images you have, your standard error starts decreasing. But at
Yeah.
least you can
So
explain it through, you know, physical math, or not physical, but like experimental error. Whereas if you start putting spline on things, remember the question I always ask people:
why
why do
not?
you believe this spline is true? Why is this function?
And
Does
so
this represent anything physical?
yeah, gosh, and because initially I went down that path, and so the question it became, because I have some data. This is the data after I already not normalized the data. I separated the data because sometimes you have, for example, you have velocity vectors stacked on each other. You can have
Mm-hmm.
velocity vector measured at position 60, and then there might have been a velocity vector also measured at position -60, but it was further downstream from the orifice. So I had to separate those a little bit and offset them so that I could computationally go through that, like essentially average them to get
Yeah.
average those vectors together. But I just didn't like having that area of unknown, and not having that area of unknown being non-uniform around a point. So for like at position 60, how big of an area does that cover until I get to the next point where I have data? And you mentioned something, a trapezoidal rule. I'm not familiar with that.
So the trapezoidal rule is okay. So let's say your first point is. Can you see my cursor?
Second here. No, I just see a picture of you,
Okay.
unless you do
Oh,
screen.
okay. No, I don't have your thing. But let's go back to your picture real quick. I lost the
Okay,
image.
there we go.
Okay, so in the trapezoidal rule, let's go from your 0
Okay.
example.
Yep.
So right there at that point, what's the closest point next to it? To the right, to the negative portion. Sorry.
To the negative portion. So you got. I don't
Mhm.
have any point on 0, but I got 2 points really, really close together, and they're approximately the same value.
Okay, so let's go with that negative. Let's like I don't know. That's like 2,
Yep.
and then the next closest one looks like -16 or something like that.
Yep.
So you draw a line between those 2 points, and then under that area, right? So you have a straight line, and
Yep.
then under that area, that straight line is a trapezoidal rule. So it makes a trapezoid.
Okay.
So that would be one integration, right? So you have one trapezoid, you know the area of that trapezoid. Then you would go to the next one, and it looks like 17, right? So from 17,
Oh, so you just
16 to 17,
integrate
you
the
have
area of the
a,
trapezoid.
yeah. So
Okay.
your trapezoid can be of any size.
Yeah, and that makes sense for discrete data points because, like you said, the slope of the line is going to be different,
Right,
and so
right.
that's
You'll
how.
have a ton of these weird trapezoids with very varying or with highly varying slopes,
Yep.
but that's okay because you just look for the area. So
Yeah.
in essence, it doesn't
Okay.
really bother you as much. And then
Excellent.
there's also like the averaging of the trapezoid rule. So you do all the trapezoids, and then you say at the center of the trapezoid is the middle, right? That's the average between the 2 points. And you take that point and then spread it across the two areas, or I'm sorry, the 2 points to make your area, and that's called the averaging trapezoid.
So
So
after
that,
after I integrate, I got to find the average area between the two not correlated, but two trapezoids essentially coincident together that are sitting next to
no,
it.
you don't have to do that, but that's just some people. That some people do that instead.
I see.
It's one or the other. And I think for your case, I would just do the simple trapezoid rule.
Yeah.
And I think you're going to come out. I mean, I'm just eyeballing it, but it looks like it's going to come out fairly okay. And if I'm really reading this data right, it actually looks very symmetric on both sides.
It does. It's actually behaves very symmetrically. I mean, I got one outlier at about -52, where I got my cursor on it right there.
See, to me, that's not an outlier. To me, that's a data, because if you look on the opposite, almost at -50, yeah, that guy.
Yep.
It it looks like it's a repeat, and it's
Yeah.
from 27 till 22, so a difference of 5 meters per second out of 20-ish, so that's 25%. That's probably well within your error.
Yeah, outlier was a wrong term. It's just a data point that's
Yeah, when
above.
you say outlier, that means like you're gonna throw it away. I mean,
No,
that's not an
no,
outlier.
I don't. Yeah, and well, and it's. I went back, and the streak is legitimate. It's there, and it's well within, and it's not very far from my orifice diameter. Oh, and I forgot to tell you, this is just the x component of the velocity. Since I'm only worried about entrainment, entrainment's only
Mhm.
primarily going in the x direction. Because I looked at removing the bias. I should have started with this. I looked at removing the bias, but all my bias is dominated in the y direction, and so mathematically speaking, it just drops out from the from
But
the
as you get away from the orifice, you're gonna have to account for that, right?
uh
Because you're gonna be coming in at an angle, and the further you are away, the sine of that angle becomes larger, and it's no longer close to one.
so I hadn't we talked about going away from the orifice just to check, that the velocity, the particles are moving well with the flow compared to the
Yeah.
streaks. But in terms of actually calculating orifice entrainment, I didn't think about. I wouldn't go further away from the orifice because essentially that's where I need to be.
But don't you get better data the further you are out? I mean, the particle is more discrete as opposed to a streak.
Yeah, they're more particle, but um,
Wouldn't
that's
that help with your error if you had more particles and bigger flow fields with less streaking and more discrete particles?
would it help with my error? I don't know if it would help with my error. It is more data. The question is how
Well,
does it
error is is the standard deviation or your standard error is divided by the number of samples you have.
yeah. But you're moving, downstream away from the orifice, and
Oh,
so
I know. There's a penalty to pay, and I would think that maybe 2 or 3 diameters would be the end.
yeah,
So for most people, when you look at flow fields in a PIV flow field, usually they go by some sort of measurement, and that measurement is the physical object. So if you're doing like a wing, they would go maybe a quarter chord is kind of like the where the good region is of interesting flow is. Half chord is considered transition. A full chord is considered the flow away from the object,
yeah,
right? It's back into some sort of um, no longer transient based on your object.
yeah. Well, and so and it's also interesting. So I got to think about data analysis because every shot that I go, just stepping downstream away from the orifice, respect to where I hit on the laser sheet, it can add a layer of difficulty. Whereas if
Yes.
you're really 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 close to the orifice, as in this example here, I mean, it's yeah, I'll have to play around to see what benefit I have from an error perspective I get from moving away from further downstream from the orifice.
Yeah. And again, that's the rule of thumb. I mean, I'm not sure I can apply a rule of thumb for you, but it would be worthy for you to explore that so that you can have confidence,
Yeah,
right? And that work wouldn't be wasted. You could show that confidence, as a matter of fact, because you can calculate that error and can say, hey, as I'm moving 2 diameters, let's say, the error is so large that it overcomes my flow
yeah.
field. But as I get closer and closer, let's say half a diameter, although I have more streaks, I don't have spatial understanding. My confidence that this value is being more and more true.
Well, so here's what I'm afraid of moving away from the orifice is we don't know what the velocity profile looks like. And the reason I went so close to the orifice this time because you're the closest to the source. So the question is, so I'm essentially at a half a diameter downstream from the orifice. If I move, let's say, a full diameter downstream from the orifice, the particles further downstream are moving slower. But the question is, how I don't know what I should expect them to be relative to the actual free stream velocity into the orifice. I don't know what that velocity decay is supposed to be as I move downstream from the orifice. I mean, I could look at fully formed jets and other type of flow devices, but there isn't really anything that I would feel comfortable from a calculation perspective to actually apply to this research, because it's
But you're not calculating the flow field. You're calculating confidence. So if you're far away from the flow field and you have this weird jump of data, then you don't have good confidence. But as you start progressing further and further away, and you start seeing this nice decay, then you can report to the committee that you have confidence in your technique as you get closer and closer to your point of interest.
I see. So I'm not actually moving away from the orifice to measure the flow field. I'm moving away from the orifice to paint a bigger picture that the technique is working.
Correct, because you're providing to the committee something that hasn't been done, and so the question would always be, how is your technique? Do we trust or believe that what you're doing is accurate and follows, some understanding of the things that we already know? So how do you do that? Confidence. And as you progress through this technique, you need to show confidence.
Okay, so now I understand why, because as expected, you move away from the orifice, that slows down.
Mm-hmm.
So I need to. That's okay.
And you only need to do that like once or twice in your thing just to show the confidence interval.
I thought I was moving away from the orifice to get more. When you were saying confidence on the actual true entrainment velocity through the orifice, and so yeah, it's all about technique validation.
Correct. I mean, at this point, you need to validate the technique, right? So you're writing the story for your committee, right? I want to measure something. It's never been measured. I'm coming up with my own technique. Now I'm going to show you why I believe my technique is good and how good is it really, right? And then you say, now that I've proven to you that my technique is this good, here is what I can gather from this technique to show my problem. So you finish that circle.
Yeah, and so yeah, I validate the technique, and then after the technique's validated, it's like a torque wrench. You calibrated your torque wrench. After you calibrate your torque wrench, you can use it.
Now you can use it anywhere to torque your nut.
Yeah.
Because you have a good understanding of how good it is and where it's good at. So for instance, if you kind of come to the point where you have this weird transition, let's say a 1 diameter, which I don't know if that's true or not, but let's just say you have a weird jump in this 1 diameter. Then you kind of have some understanding to say, far away, I think the answer is good, let's say. But when I get to like half a diameter, I start getting these weird jumps in velocity. So now I don't know how good my data really is. So here's my line I'm going to draw. I'm going to draw that 1 diameter and then calculate from there. And this is the reason why, because I have good confidence that the answer here is right.
Okay.
Or any other direction, half a diameter, whatever.
Yeah. And there's some interesting things. So you're actually looking at, so this flow field, I actually feel really, really good about this flow field, even at the center line, because I watched the video with a PhD student, Andrew Cottle, who does the UCC work.
Mm-hmm.
He's had a lot of turbulence. He thinks right after impact, there's Kármán vortices. Von Kármán vortices?
Common.
What was that?
Kármán.
Kármán, yes. And essentially the vortex shedding around a sphere. The classic is around the cylinder and it oscillates, but around a sphere is going to be in 3 dimensions. And so right after impact, or a short time after impact, like 0.8 milliseconds afterwards, in the center, you're going to have potentially a point of noisy velocity. And I still have to progress through the data, but as the flow field gets established about 1.5 milliseconds after impact, the centerline velocity normalizes with respect to the edges of the orifice, or at least appears that way qualitatively.
Well, be careful with the Kármán, because it's an actual oscillation that behaves in a certain frequency.
Yep.
And that can't be proven with the data set that you have.
No, well, it can't be proven because after the projectile impacts the shot plate and does the fluid, you're completely changing the oscillation and the fluid and essentially the Kármán vortices. But theoretically, they should be present at impact when the sphere is moving through the air.
Okay, but theoretically and you proving it is not the same thing.
No,
if you say that, you're going to answer, well, how do you know this is true? Prove it to us.
What I'm saying is,
I know what you're saying.
If somebody questions the velocity at the center line, why isn't it higher or why doesn't it look more uniform as if you would expect with established flow, is that a short time after impact, there's vorticity there that is being dissipated after impact that could be impacting the flow field.
See, I wouldn't say vorticity. That's not the right word. What you really want to say is that right next to that center line is where you have high turbulence along the center line because of an entrainment situation.
Yeah. Okay.
Right. You have a high boundary layer interaction right there at the center line, and so you're seeing the tail of that.
Yeah, because my turbulence is 8 times 10 to the 5th for some shots, and then it'll be even over 10 to the 6th moving through air.
So one of the things you can do really easy in your PIV just to show that there is turbulence there, is that you actually have that data, right? That you can show the turbulence, the oscillations in the shear.
I don't have enough field of view to show the oscillations in the turbulence.
Even in that region in the -20 and the 20, I would have thought you would have had that as you go about maybe 1 or 2 D away.
I haven't. To be honest with you, I haven't looked for it.
Okay. Because that's one of the things that Dr. Rita is going to ask you is how do you know that there's turbulence and can you show it? And I think you have the data to show it.
I thought that in other experiments with like the smoke, when I was doing the smoke shots, you can see a turbulent flow. You can't see the particles moving, but as the smoke swirls and oscillates like you'd expect in a turbulent flow.
Well, yeah, and that's because I think your particle's too heavy to be, because you have to think about the scale, right? So turbulence scales, velocity scales are U prime, whereas your flow is actually U bar. So U bar plus U prime is turbulence factor. And so U primes are usually within 5 to 10% of U bar.
Okay.
Remember that in turbulence? Did you take turbulence?
Nope.
Oh. Okay, so you calculate turbulence as a U bar, which is the velocity average along the flow direction.
Yep.
And the way people calculate turbulence is they say that U bar plus U prime, which is the component of the flow field resultant from turbulence, is equal to, or you add those together to form your continuity equations. So you have a U bar plus U prime and a V bar plus V prime. Okay. You plug those into your conservation of mass equations and conservation of momentum, and those multiples were U prime and U prime and V prime multiplied together becomes the turbulent characteristics.
Okay.
And so, because otherwise they're small, right? Unless you multiply.
Okay.
And so the point of that whole argument is that it's hard to see turbulence unless your flow is very, very, or your seed is very, very small. So that's why when you do a lot of turbulence flow field, people use smoke a lot.
Yep.
That's why they don't use particles to show turbulence.
They just flood it with smoke, and that makes sense why I saw it when I did the smoke experiments.
Yep. And that's why you would see it. But on particles, what you would see is your U prime and V prime, those small velocity scales change so they will start changing when you start seeing components as you go further and further away or further into the boundary layers. So in other words, on those boundary layers, you will see data that goes randomly more to the X or more to the Y as you would expect from the average, the U bar. Those components that you see that looks like noise, those end up tending to be the turbulent factors, U prime and V prime.
So impact was at 0, and so like you're essentially saying this noise around the impact origin is to be expected from the turbulent boundary layer, because that's how turbulence is going to show up in a particle flow field. Correct.
It will start from there and propagate.
Yeah.
That's why I believe your data is probably true.
Interesting. Yeah, because that makes sense, because turbulent, you have the vortices and all the shear layers. So depending where the particles are in that shear layer is going to be their velocity.
Correct.
So
they will shed from there.
All right. So going forward, try to use the trapezoidal rule. Get away from fitting splines, because it honestly is probably going to present more headache than it's worth.
Yeah, unless you're trying to fit a spline to show some, or not a spline, you're trying to show like a actual function, like you believe this thing looks like a u squared or a u to the third function, and then
Yeah.
you plug u squared or u to the third to show its, uniqueness relative to your flow field because
Yeah.
it's some physical phenomenon. Otherwise, when you start doing splines, you make people edgy.
Yeah. So that's, yeah, that's,
Again, if you learn nothing, you should learn that splines mean nothing.
well, yeah, and that's why we're having this conversation, is because I needed to integrate, and integrating over the flow field across the orifice makes sense for determining the m dot. Question was what to integrate, and so we came up with essentially the trapezoid.
So let me just verify your method. So you're going to do one for, let's say, at this time, and then you're going to do another one for another time. You're going to do one for another time, and then are you going to, so that your velocity function will be, the velocity is a function of, in your case, y and t?
No. After I integrate, the velocity is going to provide the velocity necessary to integrate and provide an m dot. And so I'll just have
Yeah, but you have a lot of these curves, right? Because you have one for each image you take.
correct. But the question is, so like, what v of t do I use? So like, for example, I have all this velocity data. What v of t do I use? Whereas
But
if
why wouldn't you take them all? So you would have one at t is equal to 1, t is equal to 2, t equals equal to 3. You have all these velocities, and since you're integrating them, you have m dot at 1, m dot at 2, m dot at 3.
correct,
Okay.
that's what I'm doing is because I don't have a good overall representation of the velocity. I have a lot of velocity data. That's why I'm integrating the velocity data combined with the area of the orifice and the approximate density for the m dot at this specific instant in time. But I wasn't going to actually provide an overall velocity, entrained velocity flow field. I was going to provide a entrained mass flow field.
Yeah. So when you get all these m dots, you'll have, like, let's say 10 m dots, and then you can plot the 10 m dots, and hopefully we'll see that it starts off low, goes to some maximum, and comes back, right?
Well, yeah, it should definitely come back because you'll have. I mean, there's spurt at the end of the event. There's water leaving the orifice, so the
Well,
flow
my
field.
point is, once you get all those m dots in time, you should be able to sum those and multiply time and say this is the actual amount of mass entrained throughout for the whole event.
Correct. That's
1 pound, period.
yeah, half a kilogram, whatever.
Right. So that's your hope, right?
That's where I want to get to
Okay, good.
in the near term.
And then you should be able to move like 1D away and do it again and then solve and say, hey, 1D looks like 10%, so it dropped 10%. 2D looks like it dropped 20%, blah, blah, blah. And this is my confidence.
And and so because yeah, you should roughly have, if I create a fictional boundary area, the m dot through that area should roughly be about the same.
Yeah, but here's the other thing you can do. You can plot it all in one plot, and you should be able to see the velocities decrease as you go further and further away.
Yeah.
Right, and then you can take the integral, find the m dot, and then show for m dot as a function of distance and as a function of time.
Well, my question is, as I move further away from diameters, I theoretically, from the flow field, I should also widen the orifice, right? So the
That
question,
is correct. It will be a conic shape, right?
it's going to be conical. So right now you're looking at a half a diameter in the x direction and about 2/3 of a diameter in the orifice diameter instead of the full 1D. You're looking at about 2/3 of diameter from -100 to +100.
Okay. I just want to make sure you didn't throw that data away or not process it because I think it's useful.
Yeah, yeah, because
Because remember, one of the things I always try to tell people is when you take a PIV measurement, it's not just a PIV measurement of space. It's a PIV measurement with this technique of time. And I think you need to hammer that idea home, that you're not just seeing it as one instant, you're seeing it as a function of time and space.
well, okay. I guess what was I when talking with you? What was I seeing it as?
Well, when you were talking to me about it, you made it seem like it was just a function of time and not space.
No, no, no. I especially after analyzing the data, having to write the code for it, it's definitely very apparent that the spatial component is huge.
Okay. Just want to make sure that you understood that.
Yeah. Okay. Well,
So how many more data sets do you have? I mean, is this the only one you have, or do you have many more?
I have another data set to run this technique on, to run the code on, completely independent, a completely different data set to essentially kind of compare.
Okay, like a different velocity or
Same velocity, different impact location.
oh. Well, hopefully the impact location doesn't make a difference.
That is true. So yeah, that's why it'd be good at least to run this technique on there.
Okay. And the other thing is that I heard you say that I think you're kind of already working on, but I want to verify this, is that let's say you have two streaks in the same location, like minus 60.
Yep.
I guess my question is, what do you plan on doing with that if you have 2 or 3 points on a single?
So I haven't had a problem with this yet because so far they've been on the same order of magnitude. But like say for example you had one the you have one, let's say it's like the 28 meters per second, and then on the same location, half a diameter downstream, it's at 5 meters per second.
Mm-hmm.
I have to resolve that somehow, and I'm not sure how I'm going to resolve that. But right now, all the data, all the overlap data, was right around. It was I had two right next to each other, and they're both moving. Like one was moving 5, the other one was moving 7 meters per second. And so
Okay.
what I did, average them.
Okay.
Which I think is okay on the same order of magnitude. It's the question is when you're a completely, double, a factor of 2 or maybe 3 difference. I don't know what I'm going to do there. That's
So I think there are two ways you can roll that in. My suggestion right now is to roll it into your error term.
okay.
That's my suggestion. I don't know. I have to think about it because in PIV you usually don't have two in the same space, and if you do, it's a correlation error, and you say that's you roll that into your error. But yours is so discrete. I'm not 100% sure what I would do with it either.
Yeah.
But I just want you to be thinking about it because I think that'll be a question that people will ask.
Yeah. I mean, the one thing I could do about it is, since my resolution's so high, I could separate them by a pixel. And so you have, say you have two velocity vectors on -60, you keep one on -60, and then you artificially create another column, if you would, in the matrix, and then you just shift the other vector down, and then your trapezoid would have a very, very small area under it.
Yeah.
Between those
You
two
could do
vectors.
that too because that will go into your error as well when you do that in your trapezoidal roll. That's probably legit too.
So
Okay,
yeah,
good. I just want to make sure you were thinking about it because I'm not 100% sure how I would resolve it, and I know that's a problem.
I've been spent a lot of time thinking because this is truly, I'm to the point now, outside of just general flow field and like general fluids, this is there's no place to go for help.
Well, welcome to being in the world of a PhD candidate.
Yeah.
Well, good. So, how many more shots do you have planned on to get more data?
Um, you know, after the technique's validated, I want to discuss with you what's reasonable and what's needed for the time we have left. Because because ideally I would run the gamut. I have aluminum, steel, tungsten, titanium, and I would vary all the velocities. Do a design of experiment with repetition for error purposes. But I don't. I got this weight on my shoulders of just this time crunch, and
Yeah,
since
I
so
wouldn't do that many.
since I'm spending so much time on on building this torque wrench, if you would, I don't know what is going to be good because I'm kind of in this weird area where, for example, if I was just doing PIV, right, PIV in a wind tunnel, and I was just collecting this data, and all I had to do is analyze it, my data would have to be very robust. But because I developed the image collection technique, and now I'm developing the data analysis technique for this weird flow field. the question is what does it take to suffice or keep the committee happy?
So my first on opinion is let's take a look at your error after you do these a couple of times. If your error is like what totally all over the place, the only way you're gonna fix that is by doing more. And then in which case I would just pick like, one or two top cases and just crank them out so that we can take a look at the data set and with error, right?
Yeah, because
If we go through a few of these and it looks like your error is okay by doing 2 or 3 shots, then we can reevaluate to see, based on the time you have remaining, how many different cases you want to run, to validate your model in this case.
yes, yeah. So because I'm very hesitant, to go to the lab and just start cranking stuff out and measuring stuff because we've had discussions about this. You've seen master students do it. They're just collecting data for data collection, so, for the sake of pain. And I'm not. I don't want to go down that path.
Well, that's pretty much spot on. That's not your tasking, right? Your tasking is to think about and understand what you have. A master's student doesn't really think about what they have. They just try to do more of it.
Yeah.
Right. That's what separates PhDs from master students. It's not the same order. It's not because you're there twice as long, so you get a PhD. It's the level of your understanding that grants you the PhD.
Yeah. Or in my case, of trying to identify what I don't know.
Wow.
Essentially, this is what I know. This is what I'm doing. This is the bounds of where it's valid, and then also understanding what I don't know with it. What I don't know outside those bounds. Essentially knowing where those bounds are. I guess is what I'm saying.
Well, I agree with you in that sense, but you can't have that kind of attitude going into your defense.
No.
Your attitude's got to be, I know this much, and I'm very confident in these 10 things, and then defend the things that you don't really know, logically, and why it's important, not important, or indifferent.
Yeah, and that's where the future research comes in. This is what I did. This is what I did. This is where it's bounded. And this is where essentially my area of expertise lies, and knowing where those boundaries are, I think are
okay.
important.
When you get the chance, also because I'm thinking about it, I know it's totally off topic. When they come out with the master's thesis student thesis schedules, will you forward that to me? If you see it.
Oh yeah, when they come out with the big program of who's presenting on what day and all that stuff.
Yeah. I sent an email to Renelle, but she never got back to me. I don't know if it's because my email's full or what the deal is.
Yeah, she's I think she's been in and out of the office lately.
Oh, okay.
All right. So I need to.
So do a couple more, and then the next time we talk, hopefully you'll have some error, and we can take a look at the error associated with your measurements in time and space, so that we can have some confidence about where we should go next.
Okay.
I think that's where you need to focus your time is getting your error understanding all wrapped up.
Yeah, because I can do the technique and everything, but yeah, understanding what components go into error and
yes.
what the magnitude is, I still need to work on. So
yeah, and Dr. Reeder is a big, he's a technique guy, right? So he's gonna poke at you on those kind of questions. He's gonna poke at you about error. He's gonna poke at you about your confidence. He's gonna poke at you about the actual technique in terms of mechanics of it, why it's right, why it's wrong, what are the shortcomings, what are the why is it valid? Those kind of questions I know he will poke at. Except he'll be very nice about it. He'll ask you questions like, so how do you believe, or why do you believe 10 is the correct meters per second or something like that?
Yeah.
And then that launches him into this giant thing based on what your answer is about your technique, right?
Yeah. All right. Well, I got to get writing in MATLAB again, so.
Okay.
Hey, I really appreciate your time on your day off. So. Thank you much.
No problem. Obviously, you're not taking a day off, so.
Nope. I had a good day yesterday in terms of idea generation, and hopefully it spills over to today.
Oh, by the way, when does JCAT training start?
I fly out Sunday.
Okay, this Sunday or next Sunday?
So I fly out Sunday. So yeah, this coming Sunday, and then it's in Alabama. I fly back Saturday. So.
Okay. So
hopefully,
have I talked to you about JCAT?
no, you said it's well, you talked a little bit about just the overall organization, the mission, but nothing in.
So for the training, I don't know how they're going to do it the next couple of rounds, but back in the day when I was training, I think they selected 6 Air Force guys or 8.
8.
8. So out of 8, so my class year was like 12. But anyway, out of those numbers, they only select 2 a year to be quote unquote deployed JCATers. So I don't know. I don't know what they're going to do now. So that's my kind
Yeah.
of thing to you. But what they typically do is on each after each phase of the training, the all 3 of the service chiefs, so Air Force, Navy, and Army, will get together at the end of your training week and score you. All right.
Okay.
And so every training session, they will pick their number 1 and number 2, and maybe number 3 and number 4. I don't. Oh yeah, they do, because they do alternates. So there's 4. There's 2 primaries and 2 alternates, and so they will score you the first week, second week, and third week, right? And it's not just the Air Force person that scores you; it's everybody that scores you. So my point to you is be cognizant of what you say and how you say it and who to say it to.
Okay.
And
I certainly
and
scored on both your technical and intellectual abilities, but also the way your effectiveness at communication and working as a team.
correct. And what they want most of all is the fact that you're not a jackass thinking you're better than the rest. Because when you're with the Army, which the Air Force are deployed with, you serve with the chiefs,
So
right? So they want to make sure that you don't have this high and mighty attitude where you're an officer and they're, a warrant, and you're better than them. So they want cohesion,
yeah.
right? And so they are the Army guys are especially looking for that, and so are the Navy guys, the Navy chiefs.
Okay.
And let's see, the other thing they want is your ability to communicate effectively. So the presentations that you'll give, like I think at the end of the first week there's a presentation, and then all during the second week is like every single day there's a presentation. They want to see how you handle presentations under stress and lots of questions. So you will think your answer is completely right, and they're going to barrage you with 100 things of why it's wrong. Don't get flustered. That's their job. And they just want to see how you react. If you start getting flustered, they will mark you down, because I can tell you from experience that many, many times I've gone to the brigade commander or the commanding general to tell them what happened, and I have to stick to my guns of what the facts are and what the story really is, opposed to what they want the facts are, what they want the story to be.
Yeah.
Right. So for the Army, they always want a medal to come out of it, but sometimes it's not a medal that comes out of it. Right. Somebody made a mistake.
Oh, okay. I see what you're saying. A medal, like decoration.
No, not for you. For the pilots.
No, but yeah, that's what I'm saying is.
Yeah. So you have to stick to your guns. It's the facts is the facts. And they'll hammer that to you like 100 times. The facts are the facts. And so they'll try to lead you astray. Well, what happened when this guy did this? Or is that supposed to be something that he does? Blah, blah. The facts are the facts. And then the last thing is, so the last week is, so the second week is probably the most important, right? You go to China Lake and you do all your assessments. So that's your technical skill sets and your comm. And then the last week is at TWE, and that's pretty cool, and it's pretty relaxed. And so that on the TWE one, what they're really evaluating is kind of like your team working skills and kind of how you are personally.
Okay.
Because you're kind of by yourself, and you kind of have to be able to get along with everybody when you're there. And so they just want to make sure you're not some jackass or some weirdo that sits in his room by himself. Because nobody's going to come and call you unless they know you, and they want to make sure that that's kind of your personality.
All right.
And I think that's all I have. Again, I don't know if they're going to choose like 2 primaries, 2 alternates like they did before, but I have to imagine they're going to keep score.
Yeah. Well,
these guys always keep score.
Major Pendleton and I, we went out to lunch last week.
Oh, good.
And just talking to him and stuff. It's they're working the process right now to get JCAT essentially when units deploy, that this is essentially part of the deployment package.
Yeah, they've been working on that for 10 years. So.
Well, and I mean that's news to me. I'm figuring out the system and how it works, right?
Yeah.
But it's an interesting organization and beast because it's just now getting its mission formally documented and recorded in terms of
Yeah.
what they do, what they provide, and why they do it.
Well, it's kind of cool if you get to deploy because for me personally, it gave me all the street cred I needed. I walked in there after I deployed, and nobody questioned what I was doing. In terms of the JASP organization.
Yeah.
I mean, you look at the projects that I do. I've never been questioned as to why I do those projects, and some of them are very suspect.
Yeah.
So.
Yeah. Is Digger getting ready to shoot?
He should be here on the 25th.
Okay. Good.
So.
Good. All right. Well, yeah. Well, that's another reason. I guess if you're busy, there's nothing to do but just to do it. So.
Yeah, and they actually gave me a new job at my new job. So.
You're still traveling?
Well, yeah, I'm still traveling and all that. So I was the subject matter expert in a system, and but I travel and I say things, and that's what I'm supposed to be doing. But it's as a major, you're paying me to just, mental vomit, really. So I kind of told my supervisor, because he was asking me about like how I felt about the job. I was like, well, the job is fine, but I'm a PhD and this is pretty much mind numbing. And so I probably shouldn't have said that. And so now they gave me an extra job on top of my job now. So we'll see how that goes.
So not only do you have to worry about graduating all your students, they're like, this guy clearly isn't gainfully employed, even with his additional duties. So because he told us he wasn't job satisfaction, we're giving him more work.
So yeah, and I was like, that's not what I asked for. What I wanted to do was to be a PM somewhere.
Yeah, so sounds like you're a glutton for punishment.
Yeah, pretty much. And the thing is I sit around the office so bored because my job is really when I go travel. That's really my job. And so when I'm actually at the home office, I literally twiddle thumbs. I'm doing stuff for AFIT and stuff like that, but when I graduate all these students, I could already see myself just going insane.
Yeah.
So they were like, and they're about to move people and stuff. So they were like, all right, you get a new job. I was like, damn it.
For your mental well-being, have you found the reef yet outside on the edge?
Mm-mm.
Okay, so the reef, if you go out the Shalimar Gate, it's out there. It's a satellite campus for the University of Florida, but the guys out there do partnership and research with AFRL. The building's actually provided by the Air Force, I think, and the University of Florida maintains it.
Mm.
If you could get your boss to sign off on it, you might be able to go be an adjunct professor because they have a department of mechanical and aerospace engineering, like 3 guys that sit out there that do research for AFRL, but they also teach classes.
Oh.
And so, for the sake of your mental health, maybe that might be something you might be interested in is being and as a PhD, it's probably never hurt for you to broaden your credentials and your instructor pool, I guess, if you would.
Yeah. I'll have to go. Do you have a name for that?
Yeah, I'll look it up online. I'll see if she's still there. Gosh, I can't remember off the name of my head, but she's the front office lady, but she has everybody else's schedules, and you can call her. She kind of organizes the show, if you would.
Okay. Yeah, that'd be interesting.
Yeah, and also, you could talk to them about the research they're doing and what they're doing for AFRL, because that might point you in a direction at AFRL again. So.
Yeah. Okay. Yeah. So Don for Digger's research, I don't know if you know, but he's doing that SIBR, so I help out on that every once in a while.
Yeah.
Yeah. So it's. So the funny thing is that SIBR that they're paying for, like every trial and tribulation that they've come up with, it's like I've already experienced it. It's so funny. And they don't know why, and I'm like, okay, this is why. They're like, oh, like, yeah. I told you not to do that last week. Why are you still doing that?
Yeah.
Drives me crazy.
Yep. Well, additive manufacturing has a lot of growing pains, to go through before it hits any level of maturity in terms of its applicability towards the aerospace world.
Yeah.
Essentially growing out of a toy into a full up manufacturing capability.
Yeah. I'm going to be so excited when you guys get that 3D printer.
Yeah.
I'm just going to start sending you STL files. Like, print me this, print me that.
Attach a little bit of money to it. I got no problem with that.
Oh, I see. You're already hitting me up, huh? All right.
Well, you did tell me that's what I needed to do.
If I could get somewhere more open, I would totally do it. But in the office that I'm at, that's a waste of time and effort.
What do you mean more open?
Like, if our money was open.
Oh, I see.
I can't even tell you where we get money from. That's the kind of stuff that I'm doing. So, because I asked him, I was like, "Well, we have all this funding to do this, this, and this." And I'm like, "Are these people, this thing?" I was like, "No." They're like, "All right, come back to us when you find somebody that can do that at that level." I was like, "Okay, gotcha."
Well, what happens? Because I've been there before, and so I have the clearances. What happens? I come on faculty. What's it take for me to get read in, and then you can transfer.
Let's just say we have people in the test group that aren't read in. There are people in the safety office that are not read in.
Oh yeah, I totally get that because we dealt with we dealt with our own safety review boards, safety personnel.
Yeah.
They're getting something scheduled is a giant pain because literally, to get the right person to get signed off, they might be taking 2 weeks of vacation right when the review process is, and they're the only ones that legally or not legally, I should say, only ones that can have the right clearance to view the document, to sign the document. You know what I'm saying?
Right. No, I get it. Yeah.
And so
we'll have to see.
Yeah, because I can. Yeah, I've been there before, and so I could do. I've no doubt that the clearances wouldn't go through again. So
yeah, we'll have that discussion in about 6 months.
Yeah,
maybe 7.
In the interim, i.e. today, I need to start drawing trapezoids. So have a wonderful day, and thank you once again. Thank you.
Hey, no problem. Talk to you later.
Bye.